Actually, I hope to discuss these two first, and then if we have permits time, I will move into the complex analysis and tell what are the analytic functions and so what are the Cauchy-Riemann equations and so on, right? So then actually we need to deal with these two cases. Actually, you probably heard words and you don't sometimes you don't feel what actually the hell they are. So then these were deal with actually line integrals, and these are deal with actually surface integrals. To be specific, I think this surface to be oriented, right? So it means you can clearly say what is your inside part. Inside, it means this clear. If you get a surface, you can this surface should be oriented. It means you can say what is the outside of your surface and what is the inside of your surface. So I will come back to later what are the oriented surface. So just like take an idea about. Before going to these two topics, actually, if I can say what are the curlies and what are the divergences and these how the evaluate, and there's a pretty much simple thing if you know about the gradient, right? So I will start with the gradient, right? So I think I have done some video in YouTube, so you can probably watch that. So gradient. So okay, so I'll start with that. So what you can say about the gradient? If I take, right, if I take my univariate function, right, it means univariate function means just like we do some function like real to real, right? It means sometimes some like fx, you give it a real number and it is give you out another real number as a function value. So if you plot this function, you can get the derivative. The derivative, or we usually call it slope. This actually, let's say this is f dash x. If this is coordinate, this is x. This derivative is like you make a tangent to your function at a particular point, and that slope of that tangent you can find out using this what you call the derivative. So this is we call the derivative. Okay, so this is pretty much simple for the simple for a single variable function. But if you went to onto a like let's say double variable, let's say multivariable case, what would be happening is like this is something like y and x. Let's say you have some z equals fxy type of function. It means then now you have some coordinates into each xy coordinate in this xy plane. You have some function value. This z coordinate you can get as the function value of fxy. So now how you incorporate this idea to here? It means you need to draw a tangent. Clearly, this function is going to be surface because xy is a plane now. Your function values look like a surface. But you need to draw a tangent at particular given point. Okay. So how are you going to do that? Clearly, you cannot draw a line because you can clearly if you're going to draw a tangent in this case, you just take an a point and you just draw a tangent line such that it is tangent to this function's curve. But how are you going to do the same thing on this? Here, you have a surface. So you can draw a tangent like this or this in this direction or this direction, and in any of the direction. So clearly, in this case, you cannot draw a simple tangent like this because you have multiple variables, and now your function is not only dependent on x or either y, also it is a surface. To tackle this idea, we introduce some idea called partial derivatives. Okay, so I'm not going to pretty much on the description. I just give you the brief idea what is a partial derivative means. Okay, so what we can do is, let's say we fix, let's say this function, we have function like fx1, right? This clearly you have two variables. What if I do? I consider let's say I consider some another function, right, from this. Without considering this, I consider some sort of like this function. Let's say if x and y naught. This y naught value is fixed. Now what will happen? Your function value will only depend on this variable. It means fx. Now this can you can easily represent this as gx. It means in your function you fixed your y value. Now you can only vary x. Now you are end up with a single variable function which you can do anything you do on a particular single variable function. It means you can easily evaluate. Okay, I think I have. Okay, very well. Oh, wait, wait. I think I have to. Okay, so I think you probably. Okay, now you can get me, right? I think somebody has mistakenly turned on the mic, right? So, okay, so, okay. So now you can see, right? What did happen? Wait a minute. I think. Oh, okay. Mm. I will share my screen. And I think there's something happened with my side. I think. Okay. Now you get the screen first. Now, if you fix your y value, you end up with a single variable function. It means you can vary your x value, and now you end up with your single variable function. It means you simply fix your y value. It means let's say you have a function like fxy. Let me get clear. Let's say x squared plus xy or something, right? So if you, let's say, to meet more complex, is 2y squared. If you fix y value at y naught, you can get fx y naught as x squared plus xy naught plus 2y naught squared. Remember, this value and this value is fixed. It means this whole thing is only depend on x. Okay, so it means this thing you can represent as a function of x. Why? Because you fixed your y. Then you can differentiate this thing, right? Because it is a function of x, you can differentiate this thing, g dash x. So this thing, actually, it is you differentiate your function when you fix your y. If you, let me, in other words, you treat y as a constant and you differentiate your function with respect to x. This thing we called actually our partial derivative. In partial derivative, we do nothing but we treat one variable as a constant and differentiate our function. Right? This is a simple idea, but there are pretty much interesting ideas behind it. Also, I think we can get as a partial derivative f over dabba y, we call it is a partial derivative with respect to y when we treating x as a constant. We call actually usually we read it as dabba f over dabba y. So these things are we call partial derivatives. Okay. So actually I uploaded a video about the whole thing about how these things are come, what is the geometrical meaning or another aspect of this. You can also watch that video. I will share the link with you guys as well. Or you can straight away visit to the YouTube and see that video. So then we define the function called a vector like grad f like something like this. It is dabba f over dabba x, dabba f over dabba y. This thing of it. It means our first component is the partial derivative with respect to the first variable, and this component is our partial derivative with respect to the our second variable. This thing we call as a gradient. It means this is a vector, right? So it means you can represent grad f as a vector. If you represent grad f as a vector, it's something like this. It means the portion along your x-axis or portion along your axis of a first variable is proportional to your partial derivative with respect to that variable. And portion is perpendicular or its portion is along your y-axis is proportional to the amount of your partial derivative with respect to your variable y. So this thing you call this as a gradient. So that this, if you define this gradient in this way, it has a very nice property, right? So let's say, wait a minute. Let's say something like this. Now you have gradient. So this has very nice property. Okay. So now you define a gradient. Now you have something like in the univariable case you have something called the gradient. But multivariable case you end up with something called the gradient, or sometimes we call it is a double operator or something, you end up with a gradient. So it is a vector. So now we are going to relate this derivative to this gradient. Okay. So then let's first consider as a univariable function. Okay. We draw once again we draw this univariable function. Okay. So if we take this function and if I get my x coordinate, I can draw my tangent like this. Okay. This is my tangent. Pardon of my drawing. So the slope of this is equal to f dash x. If I take a point very nearby like x plus delta x, right? Because I can represent this f dash f delta x, I know this is equivalent to actually limit delta x goes to 0 fx plus delta x minus fx divided by delta x. Or we can approximate this thing to fx plus delta x minus fx divided by delta x when delta x is very small. Okay. It means if you've taken a point very close to your x variable or this point, you can approximate your derivative using this summation. It means you simply take the difference of your function value and divide it by the difference of the variable. Now you can approximate fx plus delta x value something like this, because this is you can approximate f dash is something like this. You can approximate fx plus f dash x times delta x. You can easily see from this thing. It means this is like we called a first order approximation. Or you can simply see this is nothing but you just approximate this way. If you just get an expression for fx plus delta x, you will end up with this. From using this, what you can do is you can, if you let's say if I take this value fx plus delta x minus fx, you can take this value as f dash x times delta x. This thing you can call df. It means amount of your change of your function value when you change your variable a little bit. It means you change your x in a very little delta x value. You observe what is your change of your function value. Then you call it as a df value. You can represent it as f dash x delta x. The importance of this is, if you can also denote this as df is equivalent to f dash x dx. Okay. So very familiar thing. If you do your Riemann integration correct, you can clearly say that if you integrate fx dx, you will end up fx plus some constant, or you can omit the integral constant. You can say something like this. It means if you integrate df, okay, you can represent, you will end up with fx. It means this is your change of your function value. It is we call it a df. It means the amount of your function value change when you change your variable in a very slightly manner. Okay. So then what we can do is we can do the same thing to the multivariable function. Okay. In a multivariable function, what you can do is you have, let's say you have x, y. I take a two variable function or bivariable function, and you have grad f, which is equivalent to dabba f over dabba x times dabba f over dabba y. And we can write our df as, in this case, I will write it first and then explain what does it mean. Dabba f over dabba x plus d times dx plus dabba f over dabba y times dy. Now look at this. This thing is means when you change your variable x a little bit, how much your function value change with respect to your variable x. This portion is equivalent to how much your function value is changed when you change your y variable a little bit. It means this portion is equal to with respect to y. Now, see the beauty of this thing. You can represent this thing as grad f dot dr. If I define my dr as dx dy, it means if I take the dot product between this vector and this vector, I'll end up with this thing. It means you can still represent your df as grad f
times dr. Actually, this is the thing we use in our line integrals. It means you define your gradient, and we define our df as in this way because it is going to be equivalent to in this way. It means, let's say I draw my xy plane for clarity, right? So then you have something called xy. This is your point. You are evaluating your function. If you move a very little bit to some direction, you can take this distance as dx, and you can take this distance as dy. And you can represent this vector as dr. This is what this all means. Okay, it means you move little bit away from your point x and y, and you're gonna try to evaluate what is the change of your function, and you can define it in this way. Actually, I defined it. Actually, I think I explained it a very in a like very illustrative manner in my gradient video, so you can watch it there. So, but in the main idea is this is if you get this expression, it means it has two parts. One part is correspond to your x variable, and one part is correspond to your second variable. So with having that knowledge, you can now clearly express your df. It means your change of your function value. Why this is important? Now let's say something like this. Okay. So now we came to the inclusive movement where the curl and divergence come into play. Let's say I take my function. Let's say this is my fx. If I want to find the area between this thing and this thing, what I'm going to do is a to b. I am going to evaluate this thing a to b fx dx, because this integral is correspond to the area between these two curves. It means I integrate from my variable from a to b. It means I integrate along this line. But if you come into the multivariable case, right? If you came some function like this, say y and x. For every xy value, you have some function value. Okay. For every x and value, you have some function value. It means if you're going to integrate from one point to another, you have different ways to go. Okay. You have different ways to go. That's what we actually be discussing last time also. You have different ways to go. Then if you go some way like something like this, it means you start from one point and you go from along some path and came back to the same point, and you integrate your function along this contour, which normally we denote the c. We call it as a loop. It means we start from one point and we go from some point, go along some path and come to the point of the start of the function. If I evaluate this integral, we can evaluate this thing as, we can do this as f x y dr. Okay, f x y. Okay, so we can, it's let's say, okay, so before that we need to go to some other direction. Okay, so I forget to mention that. So now we going to move it further. For in last case, actually, you have like f x y, where this function is a scalar value. What if I have this value is also a vector? It means we can represent this as, let's say, f1 xy, okay, or fx, let's say, or fy xy, okay. So I just use f1 and f2 because otherwise you will confuse this partial derivative notation sometimes. This 1 and 2, okay. So now your function value itself is a vector. Now you take your xy plane. Okay, I take my xy plane, or and then I start from some point and I going along some path and come back to the same path. And along this path, I integrate the thing like f x y dr. Dr means nothing but you can represent this path as your function vector rt, right? Rt you can define in some way. It is defined on the path, and you integrate along this path. You simply put this notation to your integral, this little circle on your integral notation to integrate that it is a closed loop integral. If you integrate this path, what will happen to this function? How are you going to integrate these type of paths? For evaluate these type of integrals, you have some certain of theorem. That's where your curl and divergence are coming from. Okay. So is that clear, or you need to explain a little bit more, because I think people are sometimes leaving, or it's going to say it is or not. I don't think. So if it is like up to this moment, is everything clear, or you need some explanation? Okay. So you can ask. Do you need any explanation, or like it is unclear, or like it is too fast, or any comment? Or shall I continue? Hello? Hello? Okay. So I will continue. So then now look at this integral. So this is the thing you want. It means if you take some vector value function, and your a vector value function itself depends on two variables, or it can be more. And now we are going to integrate a closed loop integral. It means you start from one point and you're going along some path and come back to the starting point. So then, how are you going to evaluate this integral? Let's say one specific instance where this function, let's say your fxy, this function value itself is the gradient of some another function. Let's say some function like psi. Now what will happen? If this is itself, let's say this function value, you have a vector value function. This vector value function itself is the gradient of another function. Okay? Because you have scalar value function psi xy. If you consider this grad psi, it is going to be a vector. It has two components, right? So what if this grad psi is equivalent to this my vector value function? Now my closed loop integral is nothing but grad psi into dr. It means I can write this as closed loop integral d psi. You can represent in calculus, actually there's a theorem you can represent is grad psi dot dr a to b. You can represent this as this point a to b. This is not like x values a to b. This is our points, right? It means you have your plane, and you have point A and you have point B. Then you integrate this point from point A to B. It doesn't matter what is your path. You can write this thing as psi B minus psi A. This actually is a fundamental theorem of calculus. You can easily prove it to the one variable case, but in multivariable case you can easily prove that too. But I not bother with bother not to prove it, because you can easily see if you have something integral, you can write this thing as A to B d psi. If you integrate psi with respect to it variable, because this is one here, you can get a psi, and you simply substitute p and psi b. It means you evaluate your function value at the point b, and you reduce when you evaluate your function value at the point simple a. So then, using that thing, what will happen if my starting point and my ending point is same? What will happen if a equals b? What will happen is this integral is going to be 0. So that we call this function as a conservative function. Okay. It means if you have multivariable function or vector valued function, and you have to evaluate it along a closed loop, if you can show that it is a gradient of some scalar function, you can clearly say that it doesn't matter what is my loop is, your integral is going to be 0. It means, let's say, if it is psi xy, let's say some simple example is x squared plus 2xy plus, let's say, 2y squared. Now you can clearly say your daba psi over daba x, you can write integrate with respect to x, you can write is 2x plus 2y, and you can integrate with respect to y, you can write 2x plus 4y. And then you can write your grad psi is equivalent to 2x plus 2y and 2x plus 4y. If you have to integrate this thing, now you can write this thing as actually some vector value function, right? Fxy, because this is a vector and it is dependent on my variables x and y. If I'm going to integrate this thing over some closed loop without any hesitation, I can say that this integral is going to be 0. If I write any closed loop integral like fxy dr. This thing is going to be 0 without any hesitation because this function is a gradient of some scalar function. You got my point clear? Hello? Okay? You got my point clear? Hello? You got my point clear or you need some explanation about that? Because I feel that I don't show that I'm moving too fast or not. So if it is too fast, you can let me know that I can slow it down. Okay?
So is it fine or you need any other explanation or you have any doubt? Please tell me, right? If you don't get it, like just start, right? Don't stay if you don't get it, it is you're ready to ask questions, right? Otherwise, it is no use. Or shall I continue? Or any other problem? Hello? Hello? Okay. So I think you are silent. So if you have any problem, you can also WhatsApp me too as well. So then, you can do something like this. Now, let's look at the general case. Now you have some vector valued function and you have to integrate it over some closed loop. Okay, some closed loop. Let's say I take some specific loop to evaluate this integral, right? Not, let's say I'm not taking any general case. I take some specific loop, something like this. I get my x and my y plane, and I start with some point x, and I go to some point x plus delta x. Okay, along this is my starting point y. I going into this direction into some y plus delta y, and I go this. It means I start from here, I go to here, and then I go to here, and then I go to here, and then I go to here. Okay. So then at this moment, I can approximate my function value as f value. I represent my function value. Let's say I can write this thing as let's say now I'm going to evaluate this thing, right? I'm going to evaluate integral. It means I have to evaluate fx y dr along this path. Okay, along this path, this rectangular path. Now, what I'm going to do is, okay, so let's say in this moment, if I take in this path, right, in this path, in here to here, let's say this is capital A, capital B, capital C, and capital D. When I move from A to B, what would happen is my dr, okay, my dr is gonna nothing but some sort of dx or something, because I'm not gonna change my y variable. I'm only going parallel to my x-axis. It means my dr is I only changing my x variable. It means if I evaluate this part in this selection of A, B, it is eventually be, let's say f x y. Okay. So let's say it's something like this. Let's put dr first. It's something my function dr means dx 0 because I'm only varying my variable x. Then what will happen? I take my function value. I do something like this. My function value is also a vector. It is fxy. I say f1 and xy. Okay, it's a vector. So what will happen if I product between these two vectors, which has two components, but this vector is only having this first component. It means to my this summation, it's only required to analyze this first part. I can write this thing as f1 x, because if I can take delta x is too small, I can assume that the portion of my vector valued function this direction is like fxy. It is here. If I evaluated my first component with the portion along my x-axis is my function value. It is f1 xy. I can assume that at this portion is component, this thing is constant to x plus delta x, because delta x is too small. So I can write this thing f1 xy times dx delta x. Okay, you can write this thing at dx, and if you can clearly, if you can evaluate this thing along this direction, you can write thing as delta x, because if you can have this thing is along this direction, if you sum up the all dx distance, it means if you take dx and you get the summation of this all the, like in this direction, you can clearly, you don't have to this dx direction, you can clearly put it as delta x, because you don't have to multiply and add these things, because you can easily get, if this is constant this direction, you can easily get this thing as f1 xy times delta x. It means something like this, because you are going to integrate this guy, okay, this guy along this point to this point. What you're going to do is you take a very tiny point, it means very small distance away from your x distance, and you can evaluate this thing. Then you can easily put delta x instead of a dx, because this is a pretty much small length. So you can easily put the proportion of along this path is as fxy into delta x. Then in that moment, if you're going in this direction, you can write this thing as actually this. Now you can k in this direction, if it is f2 x plus delta x times y. Okay, this is the thing you can have in this direction. Okay, so then what will happen is you can write in BC path, you can write this thing as f2 x plus delta x times y. You can easily times delta y. Okay, you can easily take it is a delta y. Then you can easily see in here, if you go moving from here to here, you can assume that the function value at this point is constant over this point, and you can easily evaluate this as, because in this direction you can have your function value is something like this, right? Your function value is something along this direction. It is f1 x plus delta x y, and you're gonna multiply it by delta x, but your direction is reversed. Now you have minus sign. It means you connect a CD path, you have f1 x plus delta x y, and you have delta x, and you have minus sign, because in this, because the direction is reversed, right? You going into the minus direction. Then you come back to your point, your AD path. You can consider your AD path. And then in this direction, you can assume that you have function value, because it is only now contributing the component along your y-axis, because you take the dot product, your dx. Now you can have, in this direction, you can have f2 x y plus delta y. Okay, this is f2, because it is minus sign. Again, you come into the minus direction of your y-axis, and you have x comma y plus delta y and delta y. Then you can add these things. If you add these things, you can evaluate the integral, or this very simple path. You can evaluate this integral fxy dr along this very little loop. It means I go delta x distance in x direction and delta y distance in y direction. You can evaluate this thing as f1 xy delta x. I can put delta x thing forward, and f1 x plus delta x y delta x minus plus. Okay, we can f2 x plus delta x comma y delta y minus f2 x plus y plus delta y, x comma y plus delta y. Now what you are going to do is, I'm going to do something like this. I divide this whole thing by delta x delta y and multiply by delta x and delta y. I delta x delta y, I multiply. Now you can get this thing as, spot that, you can spot something like family. Okay, minus f1 fx plus delta x. Okay. Okay, so I think fx delta y, so that I think mm, so here x plus, here I made some mistake. This is y plus delta y, right? Because you move in this direction, so this thing is should be y plus delta. Okay, so this thing is correct. So then this is should be y plus delta. Okay, this is actually y plus delta y divided by delta y plus f2 x plus delta x times y minus f2 x comma y plus delta y divided by delta x. You divide the whole thing by delta x delta y and multiply by delta x delta y. Now what if I consider limit, okay, limit delta goes to 0 and delta y goes to 0, this part, right? I consider the limit of this thing when delta x and delta y goes to 0. You can easily see, you can take this thing as delta x into delta y. Okay. So you can easily see, let's say delta x is pretty much small. Let's say you don't have to take the limits and you can easily see that if you delta x and delta y is too small, so you can easily approximate this thing as this delta y, and you take minus out from this. Okay, you take minus out from this first two thing, and you will have f x y plus delta y, because delta x is too small, I just neglect that part, and f x y divided by f1, right? f1 delta y plus f2, I would say it is x plus delta x comma y minus f2 x. Sorry, I write here this something like this. I can write, yeah, x plus delta x y, and this thing is x plus y. I write this as y because I doesn't consider the difference between y, because I divide the difference of delta x. Okay, because I just simply would, because it is nothing formal, because this is not a formal illustration. So because in this case actually what you can have, I divide delta y. So it means just because it is delta x is too small, in this case actually I can neglect this delta x part. Or if you can clearly, if you see delta y to 0, actually you if you consider the delta x is very small, you send delta x limit to 0, this thing is going to be to x, right? But if you divide it by delta y, you cannot simply put delta y equal to 0. But in this summation, you divide by delta x, so you can easily evaluate this thing. If you send delta y to 0, this thing become y. But you cannot simply put delta x to 0. So you are left with this. Okay. So it means this thing is simply equivalent to daba f1 over daba y. This thing is equivalent to daba f2 over daba y. Now the strange thing is happening. Okay. So you can approximate this integral by delta x, delta y times daba f2 over daba y minus daba f1. Sorry, daba f2 over daba x, right? This x, daba x, and this is x, and this is y. So now nice thing is trying to happen, right? f2 over daba x minus daba f1 over daba y. Now clearly see what does this thing mean? Delta x times delta y. What does this mean? It is the area of this rectangle. Right? The area of this rectangle. Okay, this is actually area of my rectangle. Okay, so what does this thing mean? What is the hell of this? Now, let's say I say something like this. I take the determinant of this matrix, daba over daba x, daba over daba y. I just treat them as some elements of a matrix, and I put f1. Right? If I take the determinant, I can get this thing as daba f2 over daba x minus daba f1 over daba y. It means I represent this daba x over times f2. I denote it as daba f2 over daba x. It is in calculus. You clearly, if you use daba operator as some, if you multiply with this thing, actually it means you apply the partial derivative operation on this thing. If you multiply these two means you differentiate your f2 function, this because these two are functions, right? X, y, right? These two are functions, right? So it means you apply differentiation with respect to x on this function value of 2. This is the thing we got. We can denote this as, if you consider my grad as a vector, something like this. We can denote this as grad cross f. It means if you denote your grad as a vector like this, if you denote this grad as vector as this, because we know you can represent, let's say you take some vector, it means a1, a2, a3, something like this, and you get some b vector, b1, b2, b3. How are you going to find this cross product? You simply take I, j, k. Okay, so you take the determinant, right? So simply you can do the same thing as this. You can take the cross product of this, because simply it's the determinant. You can get this summation by taking the cross product. Let's say it means you define your gradient as this. Your function value is actually f1, 2. I'm not writing the variables. Now you can take the cross product, right? If you take the cross product, ijk, this daba x, daba y, and I have nothing to, it is f1, f2, and c. And you end up with the result f2 over daba x minus daba f1 over daba y times your k. What is this k? K means a vector perpendicular to these vectors. Okay, it means vector perpendicular to both I and j. It means I can take this thing, I can write this thing as something like this. Grad your function value, take as a vector, and you multiply by the vector k. K means actually the vector perpendicular to your both of these vectors, right? So this is actually you called a Green's theorem, right? Green's theorem. It is actually nothing. If you can, it is actually, if you can tell, if you can get this small, like small area, it means you travel small distance along your x-axis, and you travels very small distance along your y-axis, and then you trying to your loop integral along this very small loop, what you will end up is something like this. It means if you divide this thing, xy dr, you can evaluate this thing as grad cross f, right, dot k times dA. Okay, it means if you take the, it means actually in my case it is actually dA. My dA means nothing but dx into dy time to dy. It means very small, dA means very small area. Now what is the important of this? It means now we have some result. It means if we take my xy plane, right? If I take my xy plane, right? It's actually pretty hard to explain. It's a very small time period. I'm trying to do my best, right? So it is something like this. You got x and x plus delta x, and y is actually here, and you have here y and y plus delta y here. Okay, so y plus delta y here, it is y here. So it means you have some very small constant. It's nothing but you can represent this as a rectangle which has side length of delta x and delta y. Now consider arbitrary loop, right? Now consider any arbitrary loop. Now what will happen if I consider any arbitrary loop? I trying to consider this small pieces together inside this arbitrary loop. I'm trying to fill this. It means I divide this loop along to very small rectangle. It's I consider the area like covered by this loop to very small rectangle. It means I divide this small area. Now I try to get some relation from this, because in this kind of loop I have the result. It is grad cross f delta x delta y. It is okay if I can put grad cross f into dA. dA means nothing but the area of this curve. So let's say if I can fill this up, I say I can calculate the loop integral. I say, so how it happened? Let's say you have one loop like this and you take another loop like this. Okay, so it means you evaluate your function value in this value, this value, and this value, and this value along the same direction. And you evaluate your function value also start from here in the same direction from this loop as well. It means you go here to here to here and here. Happened in this path. When you evaluate in this path, you go in this direction. But evaluating in this path, you will go in this direction. It means this path is cancelling out. And it turned out to be if you evaluate in those two rectangles separately and add them together, you will end up with your integral correspond to this large perimeter, right? Because this thing is cancelling out, because one time you move in this direction and the other time you move in this direction. So in the same way, if I have very small, let's say very small area like delta x and delta y, which we call our elementary area in previous case, I think I explained it in the last Kuppi as well. If I know the result, the integral over this very small loop dA, if I can sum up all the small loop inside this area on my desired any loop, I can get my desired result to my my integral. It means if I want to evaluate integral in this loop, like my fxy function, okay, I can evaluate this integral dr. I can simply evaluate surface grad cross f into n. This is the normal vector to the plane, and this is dA. It means now what will happen is my closed loop integral turn out to an area integral. It's integration of area. It means if you multiply this thing, you get a vector, and you multiply with this normal vector, you end up with a scalar. And what will you gonna do is you integrate over surface, because it is easy to integrate over loop. Then it is pretty much easy than the integrating over loop. You can integrate easily as a surface. It means because this is nothing but you will get up with something like gxy or something, because it is some function on x and y. Now you know how to evaluate integrals with two variables. Okay, you know how to integrate with integrals with two variables. Then you evaluate this area integral, integrate this area, and you can easily get an answer. It means this thing you can see as a function of x and y, and you will evaluate. It means let's say you have some function like fxy, and you have some function like x plus y and x squared plus y or something, right? Then you can easily evaluate grad cross f times the normal, or it is simply in this case actually your normal vector is nothing but your simple vector k, but sometimes this normal vector can be different. This is nothing but it is turned out to be a function of gxy. It is a scalar, and you get multiply with my normal vector, right? If you multiply with my normal vector, you will end up with a scalar, and you know how to evaluate these type of integrals. Last time I will do, right? Last time I do that. Okay, you evaluate these integrals because it is some sort of a surface. It means you know how to define your boundaries around this because in this case they will give you an equation for this loop, and then you can easily find what are what should be your bound for your each of these your variables to in this area. Got it? Or you need any explanation on that also? Wait a minute. Sorry for that. I received an urgent call. Okay. So then it is actually you can represent this thing. Actually, this thing we call as a green theorem. Is that clear? Or you need any explanation or like it is some unclear point because I move it very like what you call very for like fast manner, but I think it is like not effective because this is online as well because I cannot express the things in hand gestures and so on. I only thing I have is this screen. So if you have some any like clarification, you can ask from me now, and also you can. I'm not going to prove it that because if it will take another huge amount of time. If you try out to be something like this, if you try out to be something like this, because you know now what you do is actually you integrate along this path. It means you take the your function value along your path and multiply it with your distance. What if you consider the your function value is perpendicular to your path and integrate of this one? If you do it correctly, you will end up the result. You will get s grad dot f in delta x delta y. Okay, so you can easily get that. I think there are proofs available on it or with demonstration on the available. That's we call actually the divergence theorem to two variables. Actually, it is like some equal to divergence theorem, but it's not. And then you can actually extend this theorem to any of the loops. It means because so far we consider only loops is two variable functions, but you can extend this thing to loops of any variable of function. The result is called, I think, Stokes theorem or something. Actually, I don't remember the name is correctly. It is Stokes because I think you can clearly browse on the internet. Using this very basic theorem, you can prove other thing, but I think the proof is not in a syllabus. It means if you take any of the loop and you have some vector valued function to integrate of this thing, you can easily evaluate this thing by converting this to a surface integral by taking this curl and taking this normal vector to this uh, surface enclosed by this loop. Note that this surface should be oriented. It means you can clearly identify two sides. It means if you take some surface, you can identify some upper side or downside. It means you can clearly differentiate. But you can Google and see some surfaces. It means like it is some like if you take a DNA, right? Because it is like it is going around it. So then you cannot clearly identify two sides, right? It means sometimes the same side can act some inner inner surface as an outer surface as well. It means you cannot identify what you orient two sides of the surface. It means it is swapping. So you can easily see some sort of the example if you go non-orientable surfaces, right? So then it is something like this, right? In this case, actually you cannot identify two sides, right? Because if you this type of thing, because it is look like a ring, but if you look closely, it is swept, right? You cannot identify what is the inner surface or outer surface because it is swept in this in the bottom. So in this type of surface, you get non-orientable surface, but orientable surface, you can also find a normal vector. You have to find the normal vector is nothing but you can, because always you can declare a surface. There are some two rules. You can declare a surface with two variables. Or you can declare a line. Always you can declare a line with one variable. Or you can declare a volume. If you want to declare a volume, you need at least three variables. It means you can define any of volume. It doesn't matter your axis system have 100 axes. You only need to have three variables. So for surface, you need to have two variables. It means you can define any surface using some parameter vector like r, let's say x1, xy. It means within two variables, right? So it doesn't. It means you have some z, let's say y or x. This x is some surface. You can always represent it by using x and y because if you represent a surface, you are becomes it is something like this, because your r vector becomes r x y some g x y. It means your third z component, your third variable depend on these two variables. So there are no actually three variables. You can only have two variables. So then you can find the normal vector to this something like this. It is x rx times to ry. It means you take the two variables and partially differentiate with this. You take it means you when you have two variables, it define your function. It is your r variable. Then you can take the differentiate. It means you differentiate with d. It means you differentiate this dr into dx, and you differentiate dr into dy, and you have two vectors which is, it means in the way you gonna take this means you can denote this as rx and you can denote this as ry. It means your moment of change of your vector valued function with respect to those two variables. If you get this cross product rx and ry, it is going to perpendicular to your surface. Actually, that's what we did when we evaluated some functions like rt, something like xt and yt and zt, right? So we evaluate our tangent vector and normal vector and so on. So in the same manner, if we can evaluate, because it means if let's say if you have some surface, you have some vector r x y. It means if you take r dash x and r dash y, these two vectors should lie in this vector itself, because if you change a little bit, your vector should go along your surface, not above the surface or not. So if you take this cross product ry, this thing will definitely should be normal to your surface, because these two vectors are two vectors on the surface. So then you can get a vector normal to that surface taking the cross product of those two vectors. Okay, you got the point? Hello? Or you need any explanation? Okay, ask. Someone unmute.
Hari.
Okay, so is that thing in the multiple variable case? So then you have to actually then you have to divergence theorem. Actually, I'm not going into much forward on that. So basically now I'm going to summarize what we discussed here, and I briefly state what the divergence theorem is mean. Let's say you have any function, let's say vector valued function f x y z rho, and it usually you have functions only three variables. Now then they will give some curve or some loop to evaluate this integral, this closed loop integral f x y c d. So you know how to define this dr. I discussed in the previous section, so I'm not pretty much touch on that. So if you want to integrate this thing, what you're gonna do is you need to evaluate this thing, and you need to evaluate a normal vector to the surface enclosed this your closed loop. Then you can get this integral by simply evaluating this thing, grad cross f dot n d a. Okay, so this thing is going to be scalar because this is a vector and this is a vector. Dot product between two vectors going to be a scalar. So now the other thing is, actually this is we call right. This is nothing but double integral. You know how to evaluate double integrals, and we discussed in the previous session. That's why I say if you know how to evaluate double integral, there's nothing more you should do in curls and divergence. You need to calculate this integral. What should your integral, and then you can proceed the knowledge on the double integral itself if you properly know how to apply your curl and divergence. Curl is nothing but, it means you can k I j k. You can take daba over daba x, daba over daba y, daba over daba z, and you can take f1 over f3. It means you can represent your vector valued function as this one. Your component along x-axis, your component along y-axis, and your component along z-axis. So this is, if you evaluate this, it means you treat your gradient as a vector like this, represent your function as a vector like this, then you perform the normal cross product between two vectors along this the gradient and your vector valued function. And then if you have
let's say, I think you should, then you have, let's say you have some volume, something like this. You have some closed surface, let's say this is a closed surface. It means something like a balloon, let's say, something like a balloon. So it has some inner surface and outer surface. And then you need to evaluate, you have some vector valued function f, x, y, and z. And then you need to evaluate f dot n ds. It means you need to evaluate your function value and the dot product between the normal vector to this oriented closed surface and this along the closed surface. It means you take like balloon or something. You need to you take the normal vector to the balloon surface to the outside, and then you need to evaluate the dot product between your vector valued function and that normal vector along your surface. You can evaluate this thing using this integral grad dot f dv. This is actually going to be like going to scalar. So what you're going to do is actually you got between the normal vector and your function, and you're going to evaluate your surface, and you can easily convert it to a volume integral. It means you're going to integrate over the volume enclosed by this surface. Your this product is nothing but you can represent your grad as dab over dab x, dab over dab y over dab z, and you can represent your function value as f1, f2, and f3, and you can simply perform the dot product as f1 daba x plus daba f2 over daba y plus daba f3 over daba z. So then if you evaluate this one, this is nothing but this is something like g x y z. It is a normal function. It's all is left is a triple integral. Okay. So the relevant theory is done in the previous section. This is actually highly useful when you analyze electric field. I think electrical students and both electronic students have this module in fourth semester, right? Electronic students have electromagnetic. This electromagnetic is the module's name. I think the electrical students, they have something called electromagnetic field or something. So this thing, the curl is actually important in magnetic field. In the postulate, right? Because it is really important if you know this thing like really well in this semester, because otherwise you will in the next semester in the electromagnetic model, because they are the applications and they will clearly use these concepts to derive the formulas, and all things depend on the curl and divergence in the electric fields and the magnetic fields, and also in the wave theory if you try to the electromagnetic waves and so on. Okay. So is there anything to add, or you need anything to ask? You can ask. So I think it is actually it is all thing about the divergence and so on. Actually, I think I moved too fast as I suppose. But if you need to anything, you can ask now. If you have any doubts about the theories and what are the divergences, if you have like some sort of like doubts or like unclear points, you can ask now. So I think it is the best way to continue. I think in the complex analysis, I think there's a whole another part. So we need probably need another day. And also I will share the recordings of the previous which I done for the 18th but I think there are 2 sessions that I did. But it is also actually the brief. Actually, if you need to understand those, what are the partial derivatives, what is the gradient is, and what are the uh, oriented surfaces are, and how to what these things actually mean. Actually, you will need more time. Actually, it is around 2 to 3 months. Actually, you will need at least to get understand what the things are really actually mean. Actually, go beyond the syntax. So actually, it is really hard to deliver in a very short time using this only the screen and this animation, because I cannot actually use my hand even, right? Because I cannot express my facial expressions and using my hand. So I think it's pretty tough. I think sorry about that if you don't think, but if you can have any doubt, you can ask now. It doesn't matter. So there are no dumb questions. So you can ask anything. Hello.
So I think in the divergence case, it is like I just did a rough, so it is nothing but so you can easily get things. But if you are really interested, you can easily evaluate it for two-dimensional case using this notation, right? Actually, I did it for myself. So also I will share some notes on that, so you can probably go through. There are really good note I found on I think UC St. Davis or something university. I will send it to you, so you can go through it and clearly understand what does things actually mean. Actually, it means like go beyond the syntaxes, go beyond the symbols. Okay. So anything else, or can we wind up? Hello, is that all clear? Hello.
Hello, yeah. Matana Prashnak. Thank you, yeah.
Okay. Okay. So we can wind up. I think we'll need another day in complex analysis. I think in complex analysis we need to deal with multivariable limits and what are the analytic functions are and what are how we evaluate limits on the complex plane and what is the complex derivative and what are the complex mappings and how to this thing. It is really good, really massive things in your complex analysis syllabus also. So I think if you need that, I think in the last year I did just a brief, right? Because I did get only 3 hours to complete that, 2 1 hour sessions. So I think I know you have some ongoing exams as well, so I don't need to waste your time as well. So actually, really thank you for coming, and I will share this recording too. And I share the recordings of the copies on the last session, last year as well. So if you need any assistance, you can anyway contact me. If you encounter any problem with the subject matter and so on, you can contact, and I will do my best. Okay, thank you. Goodbye.
Thank you. Good night.